I'm going to do today is kind of give a rundown on what derivatives actually mean. We've done a lot of work on how to find derivatives, so how to like get the derivative function, how to get the derivative. I don't know where my notes are.
Hold on.
Did I give you my notes?
Yes.
Okay.
I will do my best.
You don't have to write anything down today.
I was-
All right, so I talked to you about how to find derivatives, how to get the equation, and how to get the number at a specific point. And let's just kind of review how we did that. Does anyone remember anything about what the derivative was, how to find it, or anything like that?
The derivative is the slope of the tangent line.
Yeah, it's the slope. Oh my gosh, the slope of the tangent line at a specific point, right? So at x equals a, okay. Anyone remember the formula to find it? Yeah, Mike.
F of x minus.
Not like this.
Plus,
Mhm.
plus
Delta.
delta x, yeah,
Uh-huh.
minus f of x
Uh-huh.
all over delta x.
Good. And it's the limit as delta x goes to 0.
Delta x goes to 0.
So that's the derivative function. At x equals a, we would just replace x with a. Okay. And it also was the instantaneous velocity, right? So we had that sort of language too. So the instantaneous velocity at that point, right? So we're trying to see how the function changes at a certain point, and we're not really looking at any points around it. Okay. Okay, so just some notation I do want to talk about. There's two different things that we're dealing with, right? We have the derivative of a function at a point, and then we have the derivative function, right? Okay, one of these is a number. Which one is the number?
X.
Okay, x is okay. X would be a number. But is the derivative of the function at a point a number, or is the derivative function a number?
At a point.
At a point, right? So this value is an actual number, right? If we calculated the derivative of a function at a point, we would get like 3 or 5 or -2 or something like that. Okay. The derivative function, on the other hand, is a function, right? So this one would be like 2x plus 1 or x or something like that. Okay. Some notation that we like to use, let's just say our function is f of x. The derivative of our function at f or at a would be f prime of a. Right, so that's what we would use to say the derivative of f at a. Okay, and the derivative function is f prime of x. Right. Okay. Another way, instead of writing f, maybe we can use y, right? Y is usually used in place of x. Okay. Another way we might want to write the derivative function of f of x is d over dx of f. Okay. And what this is saying is it's saying the derivative of f. Okay, so that's what that means. Okay, and sometimes, since we're clumping everything together, we might just, oh, sorry, f would work, but let me just use y, because that's usually more commonly used. F would be fine. Okay, and sometimes we might stick the y up top. So sometimes you might see this, dy over dx. Okay, but d over dx just means take the derivative of something. Okay. Any questions so far? All right, I think we're all good on notation. Let's just take a look at this graph here, okay? And let's think about what the derivatives actually do, okay? Now, we said that the derivatives, a derivative is the slope of the tangent line, okay? So what I'm gonna do is I'm gonna pick some points on this line, draw a tangent line, and let's just see what we can say about the slope, okay? Let me just pick this point here. Oh, that's, oh, you got an extra one? All right. So let's just draw the tangent line. The tangent line barely touches the graph. Okay, so if I drew the tangent line on this graph, it would look like this, right? So it would go up. Okay. What can I say about the slope of this tangent line? Is there anything I can say? The slope isn't going towards infinity, but the graph is. So that's a good observation. What can I say about the sign of the slope of the tangent line? Positive. Yeah, it's definitely positive because the line is going up, right? And lines that go straight up towards infinity have a positive slope, right? So since the slope of the tangent line is the derivative here is positive, right? Okay, so just by looking at our graph, I can say the derivative of this graph is positive here. Okay, so f prime of a is bigger than 0. Okay. And if I pick this point, the derivative would also be positive, right? Because we're still increasing. And if I drew my tangent line, it would be increasing. Okay. All right. Let me pick a point here. Okay, so towards the right. My tangent line would be going down now, right? Okay. Do you think the derivative is positive or negative here? Negative, right? So here, f prime of a is negative. Okay. So do you think we can all agree that when the graph is increasing, the derivative is positive, but when it's decreasing, the derivative is negative? Yeah.
You mean increase and decrease from x-axis?
No. So how the graph is, do you see how the graph is going up here?
Yeah.
Okay, and the graph is going down here.
Yep.
So when the graph is going up, derivative is positive. When the graph is going down, derivative is negative.
Gotcha. As long as we go from left to right.
Yes, as we're going left to right. Make sure we're reading, we usually read graphs like we read a book, right? We go from left to right. If you go from right to left, then it gets a little more confusing.
But with the range, you read down to up, and I've never read a book like that.
For range, you do read down to up. I can see that, but when we're reading a graph, we go from left to right, right? Mhm. Okay, so I don't know. At this point, do you think the derivative is going to be positive or negative right here? Negative, good. F prime of a is less than 0. Okay, so we almost covered all our bases here, but we haven't talked about, let's talk about this point right here. Okay, at this point, if I drew my tangent line, it's kind of straight. So my function isn't either increasing or decreasing here. It's kind of like constant. So I think Michael said it. What's the derivative? The derivative 0, good. So at this point, we're not either increasing or decreasing. The derivative is actually 0. Okay. Now I know I drew a lot of on this graph, so let's just organize this in a table. I like tables because they organize everything. So f prime of a means the derivative, right? So this is the derivative at a specific point, okay? And when the derivative is positive, this corresponds with our graph being increasing at that point. Okay, and one thing I want to make very clear is f of x is the original function, right? Okay, f prime of x is the derivative. Okay, so when the original function is increasing, the derivative is positive. Okay, now when the derivative is negative, well, f of x is decreasing, right? Okay, and when the derivative is 0, it means that, okay, my function is either constant, it's not changing, or it's turning around. Okay, so here, f of x is either constant, and remember, constant functions look like a horizontal line, okay? Or it's turning around at a. Okay, so it's either doing this or it's doing that. Any questions so far?
We have a one.
Yes. Should we just do that? Okay, so we're all good with how the derivative turns into increasing, decreasing, or constant, right? Okay. Let's talk about a graph like this. Okay, this is this is the absolute value function, right? Absolute value has the vertical bars around x. What does the absolute value function do to a number?
Makes it positive.
Makes it positive, right? So for example, the absolute value of -3 is +3. Okay, so that's all that means. I have a graph of this function, and it looks very similar to a quadratic function, except at x equals 0, I'm not really turning around. I'm instantaneously switching from going down to going up. So it's kind of like an edge, okay? Okay, well, it kind of seems like the slope of the tangent line might be 0 at 0. But let me ask you, how would I draw a tangent line at a corner? You can't, right? So when we have an edge or a sharp turn in our graph, there's actually no way to draw a tangent line here. No way to draw a tangent line. Okay, and if there's no way to draw a tangent line, what's the slope of the tangent line? Doesn't exist, right? There is no line to take the slope of, so there's no derivative. Okay, so this is an example of a function that we say is not differentiable at 0. Okay, can I take the derivative of the function over to the left? Yeah, right. So it's differentiable here. Okay, it's differentiable on the right, right? But it's not differentiable at 0. Okay, so some graphs have points where we don't have a derivative at a specific point. Okay, let's flip our page. Okay, so I do have a definition of something not being differentiable. I think we kind of understand that, but there's actually other ways our function can not be differentiable. Okay, so we talked about sharp turns. Okay, so over here we have a corner or a sharp turn. Anytime we have a sharp turn in a graph, can't draw the tangent line, not differentiable. Okay, now there's two other opportunities where we can't have something to be differentiable. The biggest thing I would say is when we don't have continuity, right? So over here we have a jump continuity, jump discontinuity, or we go here and then we jump down. Okay. At this point x equals a, there's no way to draw a tangent line because I jumped down, right? So this is another example of a discontinuity causing a something not being differentiable. Okay. The only other way we cannot have differentiability is what we call a vertical tangent line. Okay, and I know it's kind of hard to see this function, but at the point x equals a, the function is kind of like vertical, right? It looks like it's going straight down. Okay, and at this point, if I drew the tangent line, I would be drawing a vertical line. Does a vertical line have a slope? No, right? So vertical lines don't have slope, which means there is no slope of this tangent. Okay, so we have 3 different situations where we don't have differentiability: corners, discontinuity, and vertical tangent lines. Okay, any questions so far? All right.
Function that
So okay, so this is where it gets a little tricky. The graph isn't drawn very well. Let me see if I can draw this a little bit bigger. the function can be going very close to vertical. We're talking about the tangent line being vertical, right? So the function itself isn't vertical, but if I drew a tangent line, it would be, because the function is changing so fast at that point. Does that kind of make sense? So the red function itself isn't vertical. If I draw the tangent in black, it is vertical.
But that wouldn't be tangent at that point.
Hmm.
It'd have to be parallel to the point slope.
It's essentially a function. Let me draw the tangent line first then. Okay, let's draw a function where we have a vertical asymptote. Okay, and it's sort of vertical. So how about, we know the function has a value at this point, and as we get closer and closer to this point from the right, we get closer and closer and closer to this point. Do you kind of see how that it's going like that? Okay, now over here on the left, we get closer and closer and closer to this point. The function is still a function because it's changing as x changes, but it's getting closer and closer to this point kind of in an infinite way. Does that make sense? So that's kind of how we would have a vertical tangent line, because it's getting closer and closer on both sides to vertical, but it's not technically vertical. I know it's a little confusing. Does that make kind of sense? All right, how about this? Talk to me after class. I will show you a better drawing of this. I'm trying to think of a function. I think the inverse tangent is something that has a vertical tangent line. So after class, I'll show you this function that has a vertical tangent line. Okay. All right, let's keep going. So let's talk about higher order derivatives. Some other notation that you will see is, let's just say our function is f, okay, and we want to find the derivative of it. Well, I would take the derivative of my function, okay? So to make this a little bit easier to understand, I have a little chart that I messed up when I made, okay? What we're gonna do with our chart is we're gonna add an extra little category to this chart. I have my original function f. I have what I'm going to call the derivative of f. Okay, so we have an extra little row there that I forgot to put on there. Okay, let's talk about notation and words that we use to describe these functions, okay? My original function, of course, is f of x. The derivative we called f prime of x, or dy over dx. Okay. Now, if we have a derivative, that derivative is going to be a function, right? Or it could be one. I can take the derivative of that function as well, right? So what we have here is what we call the second derivative, which is essentially the derivative of the derivative, okay? So the derivative of the derivative. Okay, and it might make more sense when we go through more examples, but essentially we're doing the derivative of the derivative function. Okay, notation we use for this is f double prime of x. Okay, we're not very creative here. Okay, if I want to use what's called Leibniz notation, which is the dy over dx, you might see this as d squared y over dx squared. Okay, so whenever you see squareds in your derivative, we're talking about the second derivative or the derivative of the derivative. Okay, once I take the second derivative, I can take the derivative of that, which would be the third derivative. And I know that you're getting a little bit used to this notation. It's f triple prime of x, right? We can use 3 primes. d3y over dx cubed. Okay. What do you think the fourth derivative is going to be called? F with 4 primes? Actually, we don't call it that. So I was kind of setting you up for failure there. Once we reach the fourth derivative, we usually don't put a bunch of primes just because it's kind of hard to look at it. We'll put f with a 4 in parentheses of x. Okay, and the 4 stands for 4 primes. Okay. Another way to write this is d4y dx4. Okay, and the fifth derivative goes the same way as the fourth derivative. Okay, so we'll call this f to the fifth of x d5y over dx to the fifth. Okay. All right, let's talk about this in terms of position. Okay, so a lot of the times we use derivatives to explain the position of an object. So another way to say position is displacement. Okay, so this is the same thing as position, essentially. Okay, so let's just say our original function represents position. I talked about this before, but what does the derivative explain? It starts with a V. Velocity, good. So the velocity function is essentially the derivative of the position, okay? Anyone remember what the second derivative explains?
Acceleration.
Acceleration, good. So whenever you're asked to find the acceleration, you're finding the second derivative or the derivative of the derivative, okay? Anyone know what the third derivative is called? I remember it from high school. All right, it's actually called the jerk. That's why it's kind of a funny name, but that's what we call it. Anyone want to know the name of the fourth derivative?
Oh, you said you want to know.
Oh, you want to know, but you don't know yet. The fourth derivative is actually called the snap. It also is called the jounce. Okay, so whenever you're asked to find the snap of something at a specific point in time, you're finding the fourth derivative. Anyone know the fifth derivative? The crackle. Okay, what about the sixth derivative? The pop, good. Okay, so I just think it's kind of fun. Normally we kind of deal with the original function through the third derivative. We usually don't go up to higher order derivatives than that, but we do have some names for them. Any questions? All right. One thing I want to talk about that we will go back to, oh yeah. Yeah. Yes, I will post the no, it'll all be on my classes. Okay, we will go back to this, but I do want to talk about this just for a tiny bit, okay? When we have a graph, we looked at the first derivative and how that translates into the picture of the graph, right? So positive derivative means increasing, negative derivative means decreasing. We can also talk about how the second derivative translates into a graph, okay? And the way the second derivative translates into a graph is basically this, okay? When our function has a second derivative that's bigger than 0, so a positive second derivative, we have this thing called positive concavity, okay? So which means, another way to say that is concave up, okay? So a positive second derivative translates to our graph looking concave up. And what this means is the graph kind of looks like a smiley face, okay? That's all that kind of means. It just goes upwards, okay? So as we look at the graph, the curve is kind of pointing up, okay?
It looks like X squared.
Kind of, but it can look a little bit weird. It can kind of look like this, like half an x squared, can kind of look like this, like half an x squared. As long as it looks like the curve is pointing up, we have positive concavity. But yeah, it kind of looks like x squared. Okay. When we're concave down, the second derivative is going to be negative. So f double prime of x is less than 0, okay? And well, concave down looks like a frown. All right. Okay, so negative concavity means we have something that is pointing down. The curve is going down, okay? Now, we talked about when the second derivative is positive. We talked about when it's negative. Let's talk about the in-between, okay? So I'm not talking about the graph itself. I'm talking about the graph at this specific point in the middle, okay? At this point, we don't have positive or negative concavity, right? The graph isn't facing up or down at that specific point because it's kind of the in between. Okay, this is an example where the second derivative is equal to 0, and we say that there's no concavity. Okay, no concavity. Okay, so first derivative talks about increasing versus decreasing. Second derivative talks about concavity. So is the graph facing up or is it facing down? Okay. To make this easier for you to kind of visualize, I came up with this little chart, and I think it explains things a little bit better than looking at a graph and seeing exactly what happens. Okay. So on the left-hand side, we have a column that explains the first derivative. Okay, so remember when we see the dy over dx, that's talking about the first derivative. The rows are going to explain the concavity or the second derivative. Okay. Okay, so before we start filling in this chart, let's talk about what each kind of segment means. Okay. Dy over dx greater than 0, that means that the first derivative is positive, right? Okay, when the first derivative is positive, what does that translate to my picture? What's happening in the graph? Positive slope, or it's increasing. Good. So increasing graph. Okay. Remember, when the derivative is 0, we either have a constant graph or a turning point, right? So constant slash turning around. And when the derivative is less than 0, we're decreasing, right? Okay. Now, going to my rows, when the second derivative is positive, are we concave up or concave down? Concave up. Okay. When it's less than 0, we have concave down. And then we have that in between where we have no concavity. Okay. I want to show you some pictures and show you exactly what the graph looks like in each of these scenarios. Okay, and let's start with probably start with the first area here. Okay, so let's start at this one. Okay, if my graph is increasing, as I read from left to right, I'm going from something that's really down to really up, right? So let me just draw 2 points on my graph. Okay. As I read from left to right, if the graph is increasing, I'm starting at 1 point below the last point, right? So I know 2 points in my graph are going to look like this, okay? When I'm concave up, I want my graph to face up, right? So as I draw my graph, I'm going to be increasing. I could either increase this way or this way, right? But since I'm concave up, my graph is going to go like this. Okay, because as I look at my graph, I want the graph to face up. Okay, does that kind of make sense? All right. Okay, let's kind of skip the middle one and let's talk about when we're decreasing. Okay, I want my graph to go from left to right to look like it's going downwards. So as I read from left to right, my first point's going to be high, my second point's going to be low, right? If I'm still concave up, my graph is going to look like this, right? Because I want my graph to still be facing up, even though I'm decreasing. Okay, so this is how a graph can look concave up while still be decreasing. Okay. Let's talk about when the derivative is constant. Okay, when the first derivative is constant. Okay. If I want my graph to be concave up, well, it's got to look like this. At this point, my graph or my derivative is 0, right? I'm constant at this point. I'm still concave up, but if I drew a tangent line, the derivative would be 0. Okay. Any questions on what I've done so far? Okay. All right, let's skip the middle column first and let's do the easier one as we go concave down. Okay, so let's focus on this guy right here, okay? If I'm increasing, I'm still going from a lower point to a higher point, but if I'm concave down, what's my graph gonna look like? Gonna go kind of upside down, right? It's gonna look like a frown. So my graph is actually going to look like this, okay? And of course, my graph is going to be facing down, okay? All right, let's focus on this cell here. If I'm decreasing, I'm going from a higher point to a lower point. If I'm concave down, how's my graph gonna look? Let me do this. A or B? Which one? A, good. I know it's kind of hard to draw it with your hands, but it's gonna look like this. Okay, so we're still decreasing, but we're concave down. Okay, now in the middle, very similar to what we did on the first column. If I'm concave down, I look like a frown, right? And my point where the derivative is 0 is right in the middle where we're turning from increasing to decreasing. Okay, and my graph is still facing down. Okay. Here's where things get a little bit harder, okay? We are going to talk about what graphs look like when there's no concavity, and this will make a lot more sense when we go further into this class. Why don't we start with the middle cell? Okay, I think this is the easiest one to kind of explain, okay? Okay, let's talk about when we have no concavity, which means the graph isn't facing up or down, and the derivative is 0. David?
Does the tangent line apply to the
Yeah. So I think at this point, the tangent line is still going to be 0. Okay. All right. If I want my graph to be constant, which means the derivative is 0, it means I'm not increasing or decreasing, right? So if I were to draw 2 points, they would be at the same level, okay? What would my graph look like if I'm not facing up or facing down between these 2 points? Yeah, just a straight line. So this is an example where my derivative is going to be 0 and there's no concavity, okay? Now there's a couple other ways we can draw this, okay? If I just focused on one point, like I did on the left and right, okay? I can still have concavity where my function is kind of, or I can still have concavity around my point, but not have concavity at the point, kind of like at this point here, okay? I'm gonna show you what this looks like, and as we do more examples, I'll kind of do this. Normally, if I were teaching this, I would only show you the first and last columns, but I do get questions about this, so let me just show you what this looks like, and we'll go back to it later, okay? Sometimes we can have concavity being up and down before and after the point, but they kind of cancel each other out at that point, okay? So yes, we do have positive concavity to the left, concave down to the right, but at the specific point, there is no concavity, right? And at that point, we're not changing, okay? Another way we can draw this is the opposite way, okay? So here and here, okay? We call these horizontal points of inflection. We'll talk about that later, but this is also an example where we don't have concavity, okay? The graph can be increasing and we still don't have concavity at a point. An example of that is the example I showed you up top, okay? We can have our function kind of be going up, kind of going down, but at this specific point, we're still increasing, okay? The same thing goes with decreasing, okay? Now, I'm not going to spend too much time on this right now because I feel like we'll talk about it a little bit later in the semester, but I do want to have it here just so we can look at what concavity looks like, okay? Now, at all these points that I've drawn in the center row, we're dealing with changes in concavity, okay? At these points are kind of special because the concavity changes. We're going to call this a point of inflection. Okay, and we'll go back to this later on this semester. Okay. Any questions so far? Okay.
Is it inflection or infection?
Oh my God, I spelled it wrong, didn't I? Inflection, not a point of infection. That sounds wrong. Inflection. There we go. Exactly.
Sounds like someone talking.
Yes, that's at the point of infection. All right. So what I'm gonna have us do is we have 10 minutes left. I know that we did a lot of algebra yesterday with the definition of a derivative, okay? I'm gonna pass out this practice sheet. I will post the answers underneath the guided notes as well. And I do have the answers at the bottom of the sheet. What I want you to do is to take some time, practice with finding the derivative of these functions using the definition. I think this might give us a little bit more practice. As you'll do these questions over and over, you'll see that the steps are kind of the same as you keep doing them. So I want to kind of drill it into your minds on how to do these. Okay. So before you get started, we have two definitions of the derivative, right? We have the derivative of function at a point, which we call f prime of a, and we used this formula for it, okay? Then we have the derivative function, which is an actual function that uses this formula, okay? The only difference is that one of them has an a, the other one has an x, okay? Taking a look at number one, is this asking me the derivative of function at a point, or is this asking me for the derivative function?
At a point.
At a point, right? So we're going to use the left formula for this. Okay. Number two, it's asking us to find the instantaneous velocity function. Are we using the left formula or the right formula here? Not the left, the right formula, because we want to find the function, right? So we're going to use the right equation. Okay. How about this? I want you to work on this. The answers are at the bottom, so you can check to see if your answers are right, but you do have to show your work. When you're done, you are free to go, but I will post the answers to this on my classes.